Hi everyone. So today we're going to start on 4.2 functions of several variables. The main focus is not actually in this section is not actually talk about how to deal with function of several variable yet. To deal with what happened with a function of several independent variable, remember that's what it meant when it's a function of several variable is referred to the independent variable. It actually requires a little development. We actually not going to get to completely talk about what is the derivatives of a function of several variable until we get through to chapter 5, beginning of chapter 5. But we'll lay some foundation of what's happening in chapter 4 so that we can be ready to talk about it in chapter 5. So first thing I want to talk to you about in 4.2 will be graphs. Actually, maybe I just say graph of a function. So notice that one of the important things that you probably remember learning in calculus last year is that when we talk about in calculus, we learn to talk about try to understand what's going on from basically three different perspectives in math. Number one is algebraically. Try to study what the formula and what how to manipulate it would do, and try to understand what would happen to it. Two is numerically, meaning that maybe we'll have something that we cannot actually figure out directly through algebra. We can try to guess what happened to it by study what happened when we plug in different numbers numerically. And then the third way is to talk about graphically, where we kind of look at the graph of a function and try to understand what's going on with this function. So that's what we go kind of talk about in 4.2 about functions of several variable. We're going to try to talk about the graph and try to understand how what does it represent from a geometrical standpoint. What is the graph of a function of several variable? To do that, we're going to take a step back and learn about the following first. So in BC calculus, we usually deal with this type of function. Real valued function of single variable. So meaning function f that met from R to R. Now here's something interesting to think about. When I look at the graph of this function, what is it? So here I'm going to define this function to be y equal to f of x, which is how we typically define this type of function, y equal to f of x. In this expression right here, this is our dependent variable, which is only one. We have our independent variable, which is also only one. And then we have our name of the function, which kind of give the name to the formula that we use to relate x and y together. So example, if we say y equal to, let's say, 2x plus 3, then this is our output, our dependent variable. And this x right here will be our independent variable. And then this formula will be referred to as f of x. So the f of x will basically refer to the formula that we use to relate x and y together. Okay, and students sometimes don't think about it that way, so I'm trying to break it down so that you can understand what's going on. So now comes the interesting question. What is the graph of this type of functions? The graph, as a matter of fact, this is what happened. The graph of function f that met from R to R is a curve in R2. Now let's have to think why that is the case. Okay, so there are two things to try to understand. Number one, why is it a curve? Number two, why does it have to be in R2? So those are two things that you need to understand so that you can understand how to interpret this type of function. And the way we interpret this type of function is essential to us understanding what happened when we move on to multivariable. Okay, so first question is, why is it a curve? It is a curve, or some cases referred to as a path, or in the case right here in this example right here is a line, but a line is by definition a straight curve, which I know is kind of like, okay, those two words doesn't go together. But from a mathematical standpoint, all lines are considered to be curve also. Okay, so it is a line or a curve, or is a path or curve, because its domain has one single variable. Now, is that a surprise that is the case? It shouldn't be, because if you watch all the video from 4.1, notice that what I told you is that a function from R1 to Rm must be a curve. And the reason why that is the case, just like here, is because the function we'll talk about in 4.1 also a single variable function. Okay? Something worth writing down for yourself is that the domain, the number of independent variables, the domain actually determine what object are we drawing. And if you think about it, it makes sense, because a parameter, based on what we learned in chapter 1 and chapter 2, like with k-planes, the number of parameters define the dimension of the object that we want to represent. And the parameter, technically speaking, are the independent variables. So therefore, if you think about it, if you do have a function that met from R2, that will usually refer to us creating something that's two-dimensional instead of one-dimensional, like a plane, or more generically, a surface, which we'll talk about in 4.4. But here's how we know a function met from R to R is a curve, because its domain has one single independent variable. So now then come the next question is, why is it in R2? Because of the following. If the range is a single dependent variable, then we usually interpret the function, then the function is what we call explicitly defined. And the reason why I call explicitly defined, because we're basically defining the dependent variable strictly by all the independent variable. And because there's only one of them, so we only define the only dependent variable like that. How does that compare to parametric defined? Well, if you think about what we learned in 4.1, notice that 4.1 we have multiple dependent variable. So therefore, we refer to those as simply variable, and then the input become parameters. So now all the variable is now defined not by other variable, but now defined by a parameter. That makes it parametric. So in short, if you have single dependent variable, we define it, we call it explicitly defined. But if you have multiple dependent variable, we will refer to as parametrically defined. Okay? So on the flip side, if the range has multiple dependent variables, then the function is a parametric representation. So that's how we distinguish between how we interpret the function, both by what the domain is as well as what the range is. They both serve a purpose in different aspects of the graph. So now come the next question. When it's explicitly defined, how do we represent it? Okay, so in this case, think about the following. The graph of f that map from R to R, where is y equal f of x, is in R2 because the following, because we graph, or actually maybe I'll say the graph contains both the independent variable, which is the x, and the dependent variable, which is the y. And therefore, if you can, one independent variable, one dependent variable together make two variables. And the reason why I do that, because the graph is actually in the form of xy, which is equal to x f of x. So that is very important to understand. When we have an explicit function, we graph the independent and the dependent variables together and therefore increase the dimension that we're working with. In this case, one dependent, one independent, that make two variables. And that's how we graph them. Notice that that is different compared to what we do with 4.1. And notice that 4.1 also represents a curve, mainly because it's both 4.1 function and your function that you learned last year are both single independent variable. So they both represent a curve because of that. But because the output, one of them is single dependent variable, which make it an explicit function, versus what we learned in 4.1, which is a vector value function or several dependent variables function, which would have to force us to interpret as a parametric representation, therefore changes the way the graph worked. So in this case, the graph of f that met from R to Rm, let's say vector x equal to f of t, is in Rm only, not Rm plus 1. Why? Because it is parametric, so we only graph the output, which is vector x, and vector x is in Rm. So very important to understand the distinction between these two types of graph. Also notice that because the way that's set up, we can only use a single variable real value function to draw a graph only in R2. Any other dimension, if we want to draw a graph of a curve, we must do it parametrically. Now that mirrors what I told you in chapter 1 about lines. A line can have a standard form, which is an explicit function form in R2 only. But in any other dimension, it must be represented parametrically. So a curve works out the same exact way. Okay? Now, I guess that probably a little hard to see how the difference between the two. So how about we do a very simple example to illustrate the two ways to do it. And of course, I'm trying to show you a curve that can be represented both as an explicit function as well as a parametric representation. I would have to do in R2. Because if I do a curve in R3, I can only show it to you in parametric representation, but cannot show it to you as an explicit function. So let's talk about this example right here. Okay? Let's talk about these two curves. The first one is this one. Let's say y equal to x squared versus this one. Oh, actually, maybe I would do this. Y equal to f of x, which equal to x squared. And then here is, maybe I'll write it this way. Vector x is equal to f of t, which equal to t squared. So, first of all, you need to be able to identify which one is explicit, which one is parametric. I think it should be pretty obvious. This one is an explicit function. The reason why, because the dependent variable is y, is explicitly stated on one side, while on the other side is a formula on the independent variable. This is parametric. because it's stated that you have the parameter t, and then you do have two variables here. Vector x in this case is in R2, and therefore represent two separate variables, x and y. Both x and y are defined through the parameter t. Now let's try to draw the graph of each one of these. So what is the graph of, okay, before we draw a graph, how about we label this first? In this case, f map from R to R. In this case, f map from R to R2. Okay, interesting thing to note, both of these, it represent a curve in R2 because we graph the input and the output together, so R1 and R1 together make R2. This one also represents a curve in R2. Why? Because t is the parameter, it doesn't get graphed. We are basically graphing vector x, which a vector x is in R2, therefore our curve is in R2. So all these things you need to understand and think about, otherwise you're just going to get yourself all confused. So I'm going to try to continue to push those ideas and continue to ask you those kind of questions and hopefully force you to kind of think about it and eventually understand and remember them. Because otherwise you're just going to get confused every day. And I don't want that to happen to you. So how do I draw the graph? So simple. In this case, I'm going to just make a very simple table. I'm going to have x, I'm going to have y. And I'm going to just pick some random number. Let's say -2, -1, 0, 1, 2. There you go. So we know how that works because it's square. So therefore that would be 4, 1, 0, 1, 4. So I can now draw my graph. Here's my x. Here's my y. And everyone here should know the graph of this function. There you go. Here's my curve. And we have these 5-point kind of label on the graph. This is 0, 0. This is 1, 1. This is 2, 4. This is -1, 1. This is -2, 4. All right. So that's pretty straightforward. Nice and easy. Now let's see what happens on this side. So this side worked out kind of the same way. But except my table will look the following. We have t, and then we have x and y. So here, lucky for us is I can use the same exact same 5 x value, t value, and that will turn out to be the same exact point. And if you think about it, oh wow, that's kind of cool. Does that always happen? The answer is no, of course not. This time is only happened because our x is just t. X and t are actually the same, so therefore that's the case. So now what happened is when I draw this graph, notice that there's some sort of thing that's slightly different that we have to do. Okay. Here's my x. Here's my y. Here's my graph. Okay, there you go. All right, kind of okay. And here are the same 5 points. But this 5 point now not only corresponding to a position in space, but because we define it parametrically, we can now also define them based on the perimeter. Meaning this one is at t equal to 0, the point is 0, 0. This one is at t equal to 1, the point is 1, 1. And this is the point at t equal to 2, and the point is 2, 4. This one is at t equal to -1, and the point is -1, 1. This one is at t equal to -2, and the point is -2, 4. And also because of the fact that this go in an increasing t value, parametric curve have some kind of arrow to indicate the direction. In this case, the curve go from left to right, which coincidentally also the same as y equal to f of x, but y equal to f of x is automatically always go from left to right. So something worth writing down for yourself. In an explicit function, your graph almost, in this case, in R2, we always interpret from left to right because that's the increasing direction of x. While in a parametric representation, you kind of have to indicate which direction you're going because otherwise it will be unclear because you don't see what the t values are. Good so far? So those are two separate interpretations of the same curve in R2. Now remember what I said, I cannot do this in R3 because I cannot represent explicitly what a curve would look like in R3. Same exact reason why we cannot form a line in R3. And some of you probably already have a guess of what we can actually explicitly define in R3. But if you do, hold off and we'll talk about it in 4.4 actually. All right. Focus on single variable. Well, actually, you know what? We actually go talk about it here, I think, toward the end. Okay. Good so far? Now, then the question that often get asked would be, what is the advantage of doing a parametric then? Seem like, explicit is better because, as I always tell you, less variable is better than more variable. So therefore, explicitly with two variables is better than parametrically with two variable plus a parameter. And you are correct. For the most part, explicit is good. As a matter of fact, oftentimes we want to use explicit just simply because of the fact that we have less variable to deal with and less equation to deal with. However, there are drawbacks and there are also advantage to parametric as well versus explicit. The drawback for doing explicit equation to write a curve is that we're limited in the curve that we can represent. For example, we cannot explicitly state a function that represents the equation or the graph of a circle because it's bound by the restriction of what a function is, which must only generate graph that satisfy the vertical line test. A circle does not. Which is the reason why you learned in BC calculus, we can only represent the circle in its entirety. In parametric representation, we could do two separate semicircles explicitly to do that, but that will require you to do two functions. So it's not better. Okay, so parametric representation allow us to bypass the problem of drawing curves that must satisfy the vertical line test and be able to draw any kind of curve that we want. Okay, not to mention that parametrically allow us to draw a curve in higher dimension than explicitly would. Explicitly, equation can only allow us to draw a curve in R2, no other dimensions, R2. But parametric can allow me to draw a curve in any dimension that we choose from R2 on up. Also, another thing that's also very important about a parametric is that parametric is more similar to talk about movement along a path or a curve versus than representing a curve, which therefore means that parametrically have more application, especially in physics, where we want to talk about object moving. Okay, so keep that in mind. So now come the next question. What happened if I now try to draw the graph of a real value function, but several independent variable? So that would be what we want to talk about. So we're going to go ahead and talk about this. I have about 7 more minutes to finish this video, so we probably go finish up in tomorrow's video the more concept. But let's think about it. So now, for instance, let's say we're given a function f that map from Rn to R. So first of all, let's identify this. So f is a real value function of several variables. So first, let's identify, is this function going to be explicit or parametric? How do I know? Well, in this case, function f is explicit. Why? Because, it has only one single dependent variable. We only interpreted a function as parametric if we have more than one single dependent variable. So it is explicit. So therefore, its graph must consist of both the input and the output, because that's how we graph explicit function. So therefore, let's say let f be the function. Let's say y equal to f of vector x, where vector x is a vector in Rn. Therefore, we can say vector x is equal to x1, x2, dot, dot, dot to xn. And let's say y is a single scalar. Then the graph of f will consist of the following. Will consist of all points in the form of, that's a G, of vector x f of vector x, or x1, x2, dot, dot, dot to xn, and then you have the output y next to it. Now, think that is a vector in Rn plus 1, because that's already n numbers right here from x sub 1 to x sub n, and then now I have to add an extra output to it. So therefore, what we have here is a graph in Rn plus 1. Therefore, the graph of f is in Rn plus 1. And that definition consistent with what you learned last year, where you have a function went from R1 to R1, so therefore become 1 plus 1 is 2. And now we have Rn to R1, so therefore now the dimension is n plus 1, which is n plus 1. Now here comes also a very interesting thing. What do we draw here? What does the graph of f actually represent? So that is a big question. So let's think about it. So if you recall, I told you that the reason why the function that you learned last year, real value single variable function, as well as what you learned in 4.1, vector value function single variable. Vector value single variable function. Both of them represent a curve because of the fact that we have one single independent variable, therefore dictate that whatever drawing must have only one dimension, meaning it can only move forward and back along this graph. And yes, once again, so you often get confused. Wait, what do you mean by the curve is one dimensional? Doesn't it move up, right, left, right, up, down, and forward and back? And you are correct. A curve can exist in R3. Once again, the best example I can illustrate to you is that when you're riding on a roller coaster, you can only move along the track, either moving forward on the track or backward on the track. But as you move forward on the track, you could be moving left, right, up, down, or any direction that you choose in R3. So that's how a single variable function in R3 will look like. Okay, so keep that in mind. And so if I get confused with that, it really takes some time to get used to understanding what that means. So now comes the big question. What if we have multiple independent variables? What would that be? Well, this is what we call the graph of f represent an n-dimensional surface. N-dimensional surface. The reason why it's n-dimensional, because this n-dimensional, the reason why it's n-dimensional because it matches with an independent variable. And we call that a surface as a generic term to describe what kind of geometric object that we're graphing. And one of the reasons why we use the word surface, because in a function that map from R2 to R3, we do form a surface the way we understand it. Okay? Then what happens if it's in 3-dimensional? Wouldn't we call that a solid? The problem is, yes, a 3-dimensional object in R3 is referred to as a solid. But a 3-dimensional object in R4 or higher are not actually represented as a solid. They actually represent a surface. So let me briefly explain. Okay, but before I do that, actually, the video is already 30 minutes, so maybe we'll explain it on tomorrow's video. But the last thing I want to point out is the following. Example, if you have a function f that maps from R2 to R1, then we basically form a 2-dimensional surface in R3. And yes, a 2-dimensional surface is just basically a surface, like a plane. But if you have a function that maps from R3 to R, then we'll refer to it as a 3-dimensional surface in R4. And maybe give you one more as the last one, and then we'll end our video right here. What happens if I do a function that maps from R4 to R? Then we have a 4-dimensional surface in R5. The basic concept here is the same as K-plane, where you could have a 3-dimensional quote-unquote plane, and it doesn't form a solid, but instead it forms some kind of plane, but only because it exists in R4 or higher. So here's the same exact concept. I simply swap out the word plane with surface. The difference is a plane have to be kind of a flat thing that we imagine what a plane would be, like a line, a straight line, and a flat plane that in R2. But here we call them a surface because they could be potentially be curved. That's the reason why we use the word surface. Unfortunately, my time running out for today, so I guess we'll continue some more in tomorrow's video, on the next video. All right, talk to you guys later. Bye-bye.